important application of differentiation is that it allows us to say things about functions if we know the first and second derivative. In particular, if we know the sign of the first and second derivatives and where those go to zero, these can tell us an awful lot about what a function looks like and helps us to draw curves of functions. Let's begin by looking at what the first derivative tells us about a function. So if we look at a curve, we can identify different regions of this curve where it's doing different things. If I look at the curve in this region and in this region, in these regions, the function is increasing. Okay, so it's increasing, but what else? Well, the first derivative is positive in these regions. Where the first derivative is positive, the function is increasing. Similarly, where it's negative, the function is decreasing. So when a function goes from increasing to decreasing, if it's differentiable, that first derivative needs to go through zero. So in fact, we can identify on this picture two places where the first derivative is zero. So clearly identifying points where the derivative of the function goes to zero helps us identify these critical points where the curve goes from increasing to decreasing. So in fact, this is called a critical number of a curve. So a critical number is a point on a curve x equals c where the first derivative at x equals c is equal to zero or does not exist. This is called a critical number, and it can denote a maximum or a minimum of the function. That is, they can split regions where the curve is increasing or decreasing. So knowing where these critical numbers are then is really important for sketching a curve. Let's have a look at some examples of critical numbers. Let's take a look at the graph example of f of x equals x to the 4. This has a critical number x equals 0 since the first derivative is equal to 0. And in fact, if we look at a graph of x to the 4, we can see this corresponds to a minimum of the function. If I look at the function f of x equals the modulus of x, the derivative at x equals 0 does not exist. And this is because the function has a sharp point at the origin. So the derivative doesn't exist. We can see it is a minimum of the function, so the critical number x equals 0 still tells us something important. So those are relatively straightforward examples. Let's have another example, which is f of x is x cubed. This has a critical number at x equals 0, but everywhere else the function is increasing. So although the derivative goes to 0 at the origin, it doesn't correspond to a minima or maxima. And the reason is because the first derivative doesn't change sign. So critical numbers then can tell us whether a function has a local minima or a maxima. In fact, this forms the basis of what's called the first derivative test. Looking where there are critical numbers on the curve for differentiable functions, where they go to 0 can tell us where the function has a maxima or minima. So essentially what we do is this. If we identify a critical number on a curve that looks like this, then on the left of this critical number, f prime is greater than 0, and on the right of it, f prime is less than 0. So seeing where the first derivative goes from positive to negative tells us we have a maximum. Similarly, if I have a curve where the first derivative goes from negative to positive, then that's a test for a local minima. So where we have then a critical number, we can apply the first derivative test to see if it's a local minimum or a local maximum, or neither of those things. What about the second derivative of a function? What does this tell us about it? Well, this test tells us about the concavity of a curve. If we just look at a curve like this, then this will have the second derivative positive everywhere on that curve. And we call this curve a concave up region. Similarly, if we have a curve with looks a bit like that, then this has a second derivative less than 0, and this is called concave down. And the way to remember or to understand the sign of the second derivative and why this tells us concave up or concave down, just compare with plus x squared and minus x squared. Plus x squared looks like the curve here, looks a bit like that. And we know that the second derivative of x squared is just 2. It's positive everywhere, so it's concave up everywhere. Similarly, the function minus x squared is just a sign reversal of that, and is just x squared flipped upside down. This gives us another way of finding local minima or maxima using the second derivative of a function. So at a critical number where the first derivative of the function goes to 0, if the second derivative is positive there, then this corresponds to a local minima, and if the second derivative is negative, then it corresponds to a local maximum. If it's 0 at that point or doesn't exist, it doesn't say anything. Note to remember this, always compare with x squared to remember the signs here. What about points where the second derivative goes to 0? Well, in and of itself it doesn't tell us anything. If you look at the examples for x cubed and x to the 4 we considered earlier, those both have the second derivative equal to 0 at the origin, and that doesn't tell us whether it's a point of inflection or a minima or a maxima. However, where the concavity changes sign, this corresponds to a point of inflection, like in the case of x cubed. So let's summarize what we've learned with a picture. So say we have some function that looks a bit like this. Let's identify on this function what we've seen so far. Here we have a maximum, a local minimum. Here we have a maximum, minimum, maximum, and so on. Now, at all but one of these maxima and minima, the first derivative goes to 0. But at this point here, we have a maximum, but the first derivative there doesn't exist. There's a kink in the function. Now let's identify points of inflection. Points of inflection is where the concavity goes from concave down to concave up, or from concave up to concave down. And we can identify these here. So here's one. So on the left of this, f prime prime less than 0, whereas in this region, f prime prime is greater than 0. Somewhere in here, concavity changes sign again. And this region is concave up, since the second derivative is positive, so this maximum here also corresponds to a point of inflection. And similarly, there's another one in here. So first and second derivatives then can tell us a lot about the overall shape of a curve and where maxima and minima occur.